Welcome back everyone. In this week's video I'm designing and building power distribution switching PCBs, and I'm going to show you exactly how I did it. Alright, so here we are. I'm inside our side storage compartment where most of our utilities and electrical is located. At the bottom is one of our compressors. That's the Vi-Air compressor that feeds our whole water system. Some regulation and distribution for that. Then up here is our 180 amp hour lithium iron phosphate cells made by Caleb. This block here is all 65 amp breakers that handles the solar inputs into our SBMS solar charge controller, as well as some breakers for high current loads like our big air compressors and some auxiliary stuff. And I have some that are unused that are just mounted there as spares. Here are just some simple cheapo fuse blocks, just your Harbor Freight typical stuff, and they just have the small little blade connector fuses. And then these were supposed to be my higher current switching solid state relays. These are Photech brand 25 amp solid state relays. Unfortunately, they are fake or of such poor quality that their on resistance is so high that only about half of the power you put in comes out. And so when you're switching lights or an air compressor or anything, the lights come on half brightness, or the air compressor spins at half speed with much retardation. So those are part of the reason we're doing this upgrade today. This is our SBMS solar charge controller and battery management system. It balances all of our batteries while charging and discharging, and really slick little unit. Alright, and then top left are the SaneSmart 8-channel relay boards. I really like these for the most part. They're $10, hard to beat. They have optical isolators on each channel so that you can take whatever logic you're using, be it Raspberry Pi or an Arduino like this one, and switch whatever it is you're doing. And for the most part, I've had no problem with them. They work for most loads we have. For example, I've got the air compressor solenoid, water solenoid, which charges our water tanks. This is hard to explain. Our bumper solenoid, which pressurizes the bumper hold down mechanism. Solar solenoids that extend and retract our solar panels. Power switching for the inverter, etc., etc. And for the most part, the relays have been working great. I have had problems over here. As you can see, I've got 3 relays missing, and I've kind of hot wired some patches on there to make do. And the reason for that is our interior lights. They pull close to 10 amps, and with enough switching on and off and on and off and on and off, there's enough arc on that relay that I've just burnt them up, and they either weld themselves shut and stay on and won't turn off, or it just blows the contact off the relay, and although the mechanical relay part is switching, you can hear it clicking, it's not conducting power. Anyway, so replacing these and add a little bit of an upgrade there is a big reason for this. And then just to round this out here, this is the Raspberry Pi behind a shield, which just breaks out all my logic. 5 volt regulator, I think it's 5 amps. And this is similar to what I'm building today, although it doesn't really work for my needs. So this is a MOSFET driver board, very similar to what I'm building, in fact, but this is a N-channel MOSFET, and it originally had 4. I'll get back to that in a second. N-channel means it switches negative voltage. So the positive on your load, if it's your lights, for example, or solenoids or whatever, if it's an N-channel load, that means the positive is always connected to your lights and the negative is switched. And for reasons of manufacturing, it's a lot easier and more inexpensive to build N-channel switches like this than to switch the positive. And so a P-channel FET switches the positive, where the negative of your load is always connected to the ground, and then it switches the positive off and on. That's a lot more expensive to make and a little more complicated for some reasons, and so most of the time, little breakout boards like this, inexpensive $10 board, is going to be N channel like this. And I couldn't really find a good quality P channel board to use in here. And that's part of the reason I stuck with mechanical relays as long as I did. But I have needs, and so we're making our own. Alright, so designing the circuit. I can't be very exhaustive teaching the ins and outs of Eagle software and circuit design. So just follow along, come along for the ride, and I'll show you what I did. Alright, so let's get into the design and the software. I'm going to be using Eagle PCB, which is now an asset of Autodesk, and I've used fritzing in the past. Lots of people are interested in getting a fritzing tutorial. Its PCB layout is fine, although for more detailed and intricate stuff, I'm more familiar with Eagle, so I'll be using that. It is free to use for non-commercial purposes, as long as you keep your board under yay big. So let's get right into the software here. Alright, so very basically, this is the Eagle software. I can't get into it too deeply, but basically you come in here and you find your resistors or connectors or whatever you want to add to your circuit. Let's throw in this capacitor, put one there, and you add all the parts you need. The next step is to connect things to things. This is a regulator as an example, so I will connect the output of that to this resistor, and this resistor to this capacitor, and this resistor to this resistor, and this resistor to this connector, and this connector to that capacitor. And these are called nets, and that's just planning your schematic. So the software knows which part and which pin and which side of which part you want to connect to where. So I've just made a joke here, a funny joke, but just connect all your connections, just like you would on a breadboard. So now the software knows where all the connections are. Now we can jump to the circuit board. I need to create a board from schematic, yes. And so this is the circuit board, and this is where you lay out the parts. And this is kind of like a big puzzle. Sometimes it's fun when you get going on a roll. It can be a lot of fun to move the parts around and untangle this mess of wires. I'll just pull everything onto the board here to show you. Alright, so now all the parts are kind of on the board. I'll zoom in a bit. And these nets are those connections we made in the schematic. And you can right click to spin the parts, and left click to move them around. And you kind of move everything until you kind of untangle all the wires, because these yellow lines are the wires that we will eventually want to connect from A to B. That's kind of untangled. The next step is to make traces. Now you can auto route. I'm going to wing it. I'm going to try here. It's going to be terrible, I think. Ta-da! And that is that. It's not actually that bad. But oftentimes it doesn't make the prettiest or smartest choice. It does the best it can, and this would work. If I sent this away to be produced, that would work. But it's maybe not as elegant. The layout isn't as artsy, perhaps. So undo. If you want to route manually, this is the routing tool here, and you'll hear when I click on here to here, ding, you did a good job. Here to here, ding, you did a good job. And I don't like very thin traces because They're great if you've got 1,000 pins you need to deal with in a small board and all the rest of it. But for DIY project stuff, you're going to make an error in your board, and you need to cut a trace and jumper a trace from A to B. Any repairs become very difficult on, not very difficult, but more difficult on a small trace. So you can go up here into the width of the settings, rather the width of the trace, and make them more beefy. So this is the gist of it. You draw your lines from A to B, connecting all the things you wanted to connect in a logical way. All right, so now I have all the connections made on this silly example. Now let's jump into my board and I'll give you a little explanation of that. All right, so this is my circuit. At first it looks a little confusing and overwhelming, but I'll step through it really basically here for you. First, ground and power comes into the board and goes into a 7805 voltage regulator. It's got a 7806 part number on there, but we'll use a 7805. From there, it feeds power to the Wemos D1 Mini, 5 volts into the 5 volt input. Longtime viewers of the channel will recognize the Wemos D1 Mini as my favorite little go-to board for $3.50. They're a steal of a deal with Wi-Fi built in. Anyway, from there, the digital outputs come out and feed the ULN 2803 inputs. The ULN 2803 is a transistor array, basically a small little amplifier that takes a small signal and amplifies it to a more powerful signal. And it has ground and power coming into it as well. And then those feed out to these 8 transistors down this row. And they feed the input, and there is a pull-up resistor to each one, which I'm not going to dive into too deeply. And then a resistor and an LED for indicators, and a connector and a flyback diode, TSV. And my mounting holes in the corners of the PCB I've tied into the circuit as ground so that I can ground the whole thing just by bolting it to the aluminum backplate. And this here is the 12 volt input feeding the P-channel FETs. So there you go. That's kind of the gist of the layout. Now let's go to the board. All right, so rather than auto routing, I did spend some time and routed this all manually because it just makes it cleaner and nicer and more pretty. And in fact, some of these I/O coming into the 2803 and then out to the transistors here, I changed which I/O went to which transistor just to make this flow better. And if we go back to the schematic, you can see this notch right here. I rearranged them rather than going straight across, straight across, straight across, and straight across. If you juggle these around, then it actually makes more sense physically. And so this is my circuit board. This is the maximum size allowed in Eagle, the free version, which is 80 by 100 millimeters, I believe. And yeah, so there's the D1 Mini, comes out into the 2803. And something I didn't explain before was the dip switch bank here. I can manually just click any of those dips on and enable or turn on the circuits powering whatever is connected to the outputs. So if I have some problem with programming or need to manually override for whatever reason, I can just go and flip a switch and turn on the compressor or whatever I've got connected there. So that's what that is. And then I'll just zoom in on one of these really quick. The transistor is mounted beneath the circuit board and the connector on top, and I've done it this way to make as short of trace and as stout of traces as I can. All right, then next, once you've got your board laid out and you're mostly happy with it, we go up here to the CAM processor, and it shows the output files. It gives you a little preview, and you can see here this is going to be the top copper, bottom copper, solder mask, solder paste, etc. The solder paste is what is used to make the stainless steel stencil, which you'll see shortly. The stencil is used for spreading the solder paste onto the board. And silkscreen on the top. This is what's printed in white on the board for humans to read and drill. Everything you need here to make a circuit board is here. And so then you press process job, and it dumps a zip file with everything needed in one convenient package that you can send off to your circuit board manufacturer. All right, so once you've got your zip file out of Eagle PCB, you need to send it away to have circuit boards manufactured. I'm using PCBWay. They sponsor lots of other YouTube channels with more electronic content, although I'm in no way sponsored by PCBWay, but they do good work, so I like them and I'll recommend them. This is their online Gerber viewer. You upload the package of the zip file with all the Gerbers in it, and it gives you this great looking preview that you can go and see in color and just review that everything is as you want it to be, and then you submit your order. So historically, PCB manufacturing was very expensive because you needed to make 1,000 boards to make it worthwhile for all the setup costs and so on. And so it wasn't something the home gamer would do. And like way back in the day, I fooled around with transfer films where you would use a laser printer to print on a transparency, special type of transparency, and then you would use a clothes iron to iron that onto a copper-clad PCB and etch that way. But PCBWay, and there are other PCB manufacturers, many others, that will batch many customers' boards in one run, and then when they're broken apart, they find your boards and send you your boards. So the setup costs are distributed between everyone, and that makes it very cost effective for small numbers of boards. So I've ordered 5 of these boards. I'll see you in 3 to 5 days.
Several days later.
All right, so it's been 4 days since I placed the order, and I just received the printed circuit boards in the mail. I used the black solder mask, which I thought looked pretty classy, and all of our channel member names, tier 2 and tier 3 names, are printed right on the circuit board. So what's next? Assembly, of course. All right, so if you just have 1 or 2 circuit boards like this to get through, you can just use a syringe. So I'm using ChipQuick SMD 291AX. If you remember in our solar charge controller exploded video, I ordered this, and it's just a small amount. It comes in a small syringe, but you can use this, and it comes with a little tiny applicator needle, and you would literally just sit here and syringe dots of the liquid solder paste onto the pads that you needed to put parts onto. Since I'm doing 5 of these, and I wanted to do a good job, this is a stainless steel solder stencil, and I think it was $9 extra to add that to your order, so I went ahead with that. And as you can plainly see, it's just a thin stainless sheet with the cutouts in the appropriate places. So Eagle PCB will just export one of these for you when you process the CAM files to get your Gerbers for the PCBs. So when they ship the stencil to you, it's usually taped on to these cheap paperboard boards, and they sandwich it in the middle just so it doesn't get damaged in shipping. And I'm just going to use that as a base for a frame. So you need to get your PCB, obviously, and then every time you put this down, you've got to line it up, and that can be a little bit of a nuisance. So what they normally do is have a little holder that holds the board in the correct place. Now all I'm going to do is adjust it here so it's perfect. You can see those tinned pads are lining up with the holes in the stencil. And then I'm going to use some scrap PCB material. These are the little charger boards that I showed you guys in a video a little while ago. And there's some little scrap edges on many of these. So I'm going to get 3 or 4 of them readied here. And then I'm just going to glue them right to this board right next to this. So you see I put that there, 2 drops of super glue, 1 on this side, a little bit of that, and 1 on the top. Done. Alright, so while we're waiting for that glue to dry, I'll just give you a quick tour of the board here. As you can see here, in Todd we trust. This is an homage to my good friend and electronic father figure who's mentored me in all things electronic for years. So I put that on most of my electronic boards that we do, and Made on Earth by Humans, an homage to the fastest car in our solar system. And then all of our channel members, tier 2 and tier 3 channel members, are printed on the back of all of these boards. We really appreciate the contribution with these guys supporting the channel every month. So thank you very much. Now let's get into it. As you can see, those little fences hold the board secure enough, and when I put the PCB in there and flip this over, the pads all line up with the stencil holes. Next, you're going to need some solder paste. Like I said, I'm using Chip Quick SMD 291AX. This is leftover from my solar charge controller exploded video. And I'm just going to put this much right there. That'll get us started. And then you're going to need a Safeway card. These are really good squeegees, and they give them to you free with every purchase at Safeway. So get yourself one of those and just drag it across like this. You can see it's filling the paste pad places, and get that all in there. This stuff has dried out just a little bit, but that's all right. It'll work. You want to be sure they're all full. It's easy to miss it because it's gray on gray on gray. All right, that looks good. Flip this open. The board doesn't look too much different, but every pad has a little bit of schmoo on there. So while I have this set up, I'm going to do all 5. Next, of course, we need to place the parts. And I tend to go with smallest to largest because it's easier to get in the way with the big ones, and then you need to work around the big ones to place the small ones. So work your way from small to large is my recommendation. So this is going to be uber boring. I might live stream this to our channel members, I might not. We'll see. But I'll bring you guys in for the boring play-by-plays. You're going to need a set of tweezers. I like these curved pointy ones. And then just start laying parts down. Now, the parts, you're going to need to know where to put them and the order. Resistors are easy because there's only they're not polarized, so you can put them in any direction, either direction, and they'll work just fine. So these are the 10K pull-up resistors that make sure the MOSFETs turn off when you stop powering it. So hopefully you guys can see this nice and zoomed in on this other camera. You just place the resistors in the shmoo. You have to be 90% accurate because the solder reflow procedure will move them to the right place as long as you're fairly close. It's good to give them a little pat push them in a little bit. If it wasn't already obvious, I'm using the same board with the little fences to hold the board in place, just so it doesn't move around on me while I'm placing parts. I got all these parts delivered from Mauser Electronics, Mexico, and that worked out really well. Some of you might remember our fan or automation videos, the fan and air conditioner video. I ordered parts from DigiKey in the USA, which I've done hundreds and hundreds of times when we lived in Canada. They had overnight stuff from the US to Canada, and we'd get it the next morning for $8 shipping and no taxes, or the taxes were all prepaid by DigiKey. And so I just assumed that would be the case and ordered them up, and had to pay almost 100% tax and brokerage fees to get them into Mexico. So I was very pleased when I ordered from Mauser Electronics, Mexico, and it showed up in 2 days, free delivery, and no taxes, no brokerage fees or anything. The only downside is all the packaging, all the labels are all in Spanish, but not a big deal. 10K in Spanish is still 10K in English. All right, so next I've got the 1.1K resistors. These dim the LEDs and don't blow them up. And so they're just these. Next, the fancy LEDs. I sprung the extra pesos and ordered the Everlander orange special edition, not amber but fully proper orange LEDs. Twice the cost. Don't do that. Oh, these are not the LEDs. Those are the 2803s. We'll do them since we're here. Alright, so this is the surface mount ULN 2803. It's a Darlington array, and it's basically just an array of 8 transistors that turn on the big P-channel MOSFETs. Set it in there since we headed out. And now I've got to find my orange LEDs. Here we go. Now LEDs, of course, are light emitting diodes, and diodes, of course, are polarized. So I'm going to pop out all 8. Actually, I'm just going to do 4 at a time. Alright, so now I've got my multimeter out, and I'm going to double check the polarity on these LEDs, making sure I get them the right way around. Ooh, fancy. So, I know that this side is negative. They are marked, if you could see that small. Alright, so then the next thing you want to make sure is that you have the your orientation on the circuit board correct. So I'm just checking ground. And the ground side of all these LEDs is on the top on this side, and on the left down this row. Alright, next is the 5-volt voltage regulator. This is a nice big part, as you can see, and I'm going to use this as an opportunity to show you what I'm talking about with the solder mask, or rather the solder paste not needing to be so precise. When it flows, it goes all molten and like a bead of water on a leaf. Everyone's seen that photo. In the same way, this solder is going to go molten, and all these parts are just going to start floating and shifting perfectly into place. And to illustrate that, I'm going to intentionally place this regulator a little bit off kilter. I don't know if you'll be able, or if that'll come across in the video, but I'll turn it here. Hopefully that's still centered in the frame. And so yeah, I'll set this one off to the side quite a bit, and then we'll set up the camera to be looking at that one specifically when we go to reflow. 4, 5, 6, 7, 8. These are the big TSV that basically act like flyback diodes, and they protect the MOSFET from damage when big inductive loads kick back. You can learn all about diodes and flyback on the internet. And lastly is the little dip switch for manual override controls. Get one of these out. Put that in there. And this board is done. All of the surface mount components are on there, ready to go. And now we need to reflow it. So most solder, all solder paste, includes recommended reflow profiles. And they use these in process controlled ovens at reflow solder factories. We don't have a process control reflow oven here. I do have the hot air blower gun that I used in the I blew up my solar controller down by the river video, but I'm not even going to use that. Alright, so desperate times call for desperate measures. I'm going to use our induction cooktop. I'm going to set this to medium. Got to hit record on this camera. And then put this in there. Grab my solder profile and the best temperature sensor money can buy. 40C. We want to get up to 150C. And then hold it there for about 120 seconds. So we're sitting at 56, 57, 60. On this other tripoded camera, you can see the resistor, or rather the regulator, that part right there. It's about as close as I can get you right now. Actually, I'm going to try for closer. Alright. Monitoring the temperature still, we're at 130. We want to get to about 150, and you'll see that regulator start to float.
A little longer than a few minutes later.
You can see there that regulator just flowed and corrected itself. You don't want to rush it. You don't need to crank it to the 11 and cook everything. Yeah, the whole process should take about 4 minutes. We're getting a little hotter, 180, 190, 200. And all the solder has gone from that pasty looking flat yucky color to a metallic look to it. There's some parts over here in the corner that haven't quite gone yet, so I'll just move the pan a little bit. I see that one corner of the board's not actually touching the pan, so I'm going to push it down. There we go. That's all reflowed. And that looks good. Then you want to turn this off, put a lid on it. It's a medium well right now, but it'll continue to rise its internal temperature until it's a nice medium. Well, there you go, guys. Hot off the induction cooktop. It looks really good. I only see one little flaw on this one pin of the 2803. Didn't quite have enough solder on it, so it looks a little bit dry. I can easily touch that up with a little bit of flux and a manual soldering pen, which I will do here shortly. But first I have 4 more boards that I need to pick and place all the parts on and jump on a live stream with all our channel members and chit chat with them as we do that. So see you in a few. How critical it was for life and happiness.
2 hours later.
Alright, so today is tomorrow, and we finished the live stream with our channel members, got all of our circuit boards SMD reflow completed. Now it's time to do the through-hole components, the connectors and the MOSFETs. So let's get started with that. Alright, to solder the through-hole connector parts and the MOSFETs, you're going to need a soldering iron. Again, this is the TS100. I talked about it a little bit in our last video, and thanks to everyone who commented about getting the firmware, the open source firmware update for it. When I originally got it, I was ecstatic with all of the features it had out of the box, but there is alternate firmware, open source firmware. I'll put a link in the description, which gives a bunch of extra features like automatic shutoff, which I didn't really think about previously. But if you can set a timeout, if you aren't using it for 2 or 3 or 5 minutes, it'll just turn off until you come and press the power button again. And it also increases the maximum temperature to 450 degrees. And there's a boost mode. When you push and hold the button, it goes from your regular set point, minus 325 degrees, to your boost set point, which I've got max at 450. And that'll come in handy for these large contacts on these connectors, which are connected to big power plane and ground planes. So if you have a big heavy duty thing you need to solder, that boost is really nice. And it was really easy to do. You just plug the USB connection in while pressing the first button, the A button, and that puts it in DFU mode, or device firmware update. And then you just drag and drop the hex file to the device. It just shows up on your computer like a USB drive. And so you drag and drop that hex file on there, and then it renames it to the name of the file, .ready, RDY. And then when you power it up, it's got all these new features. So thank you to everyone who urged me to go ahead with that. I've got this ready to go. All right, so like I said, I'm going to have 3 versions of this board. And the only difference is how I finish the final assembly. The first I've alluded to already. It's going to be this super high current version, and I'm actually supplying power down this 10 gauge cable directly to the leads of the FETs. And additionally, the output pins off of the FETs are wired directly to the pins on the back of the connector. So this will be the super high power version that'll do 30 amp loads on each of those 4 anyway. And then I'm going to make a high-ish power version, which will have the leads of the FETs bent in a way that I can mount these FETs on our aluminum backplane with sill pads for heat dissipation. And then I'll have 1, maybe 2 set up with the FETs just no heat sink, and that'll be for very low current loads like solenoids and small LED lights and fans and that sort of thing. All right, so I'm going to build a medium power version now, and those are made with the FETs all laying on the aluminum backplate. And so to do that, I'm going to bend all of these leads on the MOSFETs up like this. So I'm just going to bend these all up, and then if that didn't make sense the way I said it, it will all make more sense here in just a moment. All right, now I've got the leads on the FETs all bent up, and to space them so they're spaced off the back plane just perfectly, I'm just using the standoffs installed backwards temporarily just to set the distance. And now when I place this here, I can reach in underneath, and you can see hopefully those pins pop up through the holes. I'm just going to do one side and then the other. All right, get the soldering iron fired up. And the way I like to do this is just solder one of the pins in place so that it's ready to go, and then you can bend and physically manipulate those the parts so that they're all in line nicely the way you want. I'm going to zoom this in nice and close for you. Lots of people have asked on previous videos about how I learned to solder and how to solder, and I don't consider myself a good teacher of soldering, so I'll keep it brief. But basically you want to just get your soldering iron tip as hot as you want to run it. Like I said, I've got this with the new firmware that allows the boost mode. So you can see here it's at 325 degrees, and when I push and hold this button, it'll fire up to 450. So anyway, back to the task at hand. I'm just going to solder one of the leads, put your tip in contact with the pad and the part. It usually takes a second or two to get the the heat to sink through it, and then add the solder. You never want to put the solder on your iron and then transfer it to the part. And then I like to linger for a second or two to really let the solder flow into all the crooks and crannies and get a good bond. And then you flip it over, zoom this out a bit. So as I flip this over, you can see the parts aren't all perfectly square, so then I can give it a little tweak, twist them around a little bit so they're all uniform. Then put her back down and get all the rest of the pins. Now I'm only putting a small amount of solder on these presently because this is so tight in here with the big connectors that the big solder blob here would impede the back of the plastic part on the connector. So I'm just soldering them lightly at first, and then I'll install the connectors, and then I'll come in and really bulk it up nicely. So there we go. Those four are functionally soldered, should work fine, but I will come and tune them up a little more later. Four more on this backside. Alright, now I've got the soldering iron tip. So there we go. The FET's all soldered in. Similarly, I'm going to solder these temporarily, or just put a little bit of solder to hold them, and then come back and solder them completely. And in this case, I have to cheat a little bit and do that thing I said not to do, which is because I'm holding it, if that's not clear. I have to hold this connector in place and then flip it over to try and get this all done. So just a little bit of solder and just a little bit on there. I'll show this camera. You can see there on this pin just the tiniest little bit of solder, and that's what I'd call a cold solder joint. It's bad. It's all chunky and porous, and I wouldn't trust that at all. But it is holding it in place just enough so I can flip it over and solder them properly. We'll see in the comments below if Todd would agree. And this is going to be a little bit more tricky because I have to work around these FETs, but that's why it's nice to have a very small tip on your soldering iron like this. Lets you get in those tight crevasses. And this shot is going to be really tough for Kara to get. Hopefully we can. And hit the boost button. And you don't want to start with the connector or the pin that you are holding it with, because you heat it up and then your part just falls out. Alright guys, got all 5 completed. Just haven't even tested these ones yet, but I do have a battery bank here. I've shown this before. It's just 3 18650s. Gives me 12 volts into the board. So I've got this one wired up with a Wemos D1 Mini with a very simple Blink app, and as I turn these on, hopefully you guys can see the lights down here. They're all working. So the next step is to clean these up, and I just use dish soap and a little scrubby brush or a toothbrush and scrub them up real good. The flux that I used is no clean, so it shouldn't need to be cleaned, but the solder is rosin flux cord solder. So it leaves a little bit of schmoo around the connectors. So I'm going to go through and just clean everything off with just soap and the brush, like I said, and then electrical contact cleaner, just to give them that beautiful shine. And then I'll show you what we've got. This is just dish detergent and some water dilute. Give her some of that. Also this red MOSFET board that I fixed up, and give her the scrubbies. And then a toothbrush I've dedicated for various cleaning tasks to get in all here. Alright, so my mic battery pack died, but basically I just finished by rinsing everything off really good in fresh water. Then I used compressed air to blow everything dry, make sure there's no water inside the connectors, and then I finished up with rubbing alcohol, electrical cleaner, and brake clean for some of the really stubborn flux. And here they are all finished. This is the low current version, the medium current version with the FETs on the back plane, and the super high current version, which has those 4 FETs with the 10 gauge cable running directly to them.
The next day.
The next step is to hit Control Z on this whole assembly. I'm going to pull out all of these fake Photech relays and this MOSFET driver board and maybe this one bank of mechanical relays over here and start fitting up the driver boards that I've built. Alright, got this one loosened off. As I did that, it occurred to me that I might not have explained why N-channel switching is not as preferable as P-channel for my case in automotive use, and why we're building these and putting them in here. And very simply, everything on an automobile is negatively grounded and they switch the positive. The engine is grounded, the chassis is grounded, everything is grounded, and you switch the positive connection. And that's important for me because our lighting is all positive switched. Everything is grounded to the frame or to the exoskeleton of our aluminum box, and then we switch the positive. And that's why I was using the relays. And the back of this whole power distribution board center, whatever I want to call it, is a 3/16 inch thick aluminum plate. And so for these low power versions, I can just mount them there on standoffs, and for the high current ones, which I'll be putting down here, I can use that aluminum backplate as a big heat sink. Not that it's really needed, but just as a precaution. And so that's the explanation why I need negative ground and positive switching. So I'm going to mount this one here. This is one of the low current versions, and it's just going to switch the LED lights and various other low current loads. So let's get started.
What follows is a brief construction montage. We hope you enjoyed this brief construction montage.
Alright guys, it's been a little over a week since I last did any work on this, so I have it mostly working as good as I'm going to for now, and I thought I'd give you a quick overview and tour. These 2 driver boards are connected via ribbon cables to the Raspberry Pi. I've replaced the Adafruit Perma-Proto breakout board that had the 2803s on it, because these have built-in 2803s. So I got rid of that, which looked kind of janky, and replaced it with this little speed-controlled fan hat, which is really nice actually, and then just soldered ribbon cables to that. 2 header pins that just plug in to the sockets on my boards. And then these 2 here are connected just with the Wemos boards, the Arduino boards plugged right in there, and some sample code. Just running a few basic things so far, but certainly lots of room for improvement coming up here shortly, but I'm not going to make this video any longer than it needs to be. So let's give you a big grand finale tour. Firstly, for those who don't know, we use just a cheapo $20 Adafruit wireless keyboard, and I have the F keys mapped to common tasks we need to do in the truck. So lights on and off. You can see right here that circuit coming on and off, as well as OK Google, turn on the lights.
You got it.
And this comes on. And that of course works from the keyboard or Google Voice, or in fact on our phones we've got the Blink app. Get that out of the way so you can see both here and here. And the nice thing is I can dim these now because I can. I'm not going to get into it. Your results may vary. Alright, the next thing on the list is solar. We just have two buttons here for solar in and out, and most often that's handled automatically, but I'll manually trigger it here. And the point I wanted to show was it's not just as simple as flip on one solenoid or off. It's actually running the safety lockout as well. So you'll see here on this board, when I hit the keyboard button here, both solar outputs come on, and the solar lockout, or the safety, which locks them in place while we're driving. So here's this. Solar out. So this lower one here is the pneumatic locks that lock the solar panels in, and those are the solenoids pushing them out. So that's that. All right, and I'll just show off a few things here quick. I'll put my phone app up here and show you some things. I've got the outside lights, which are the LED light strips that underneath our solar panels that we use for outdoor lighting. Light bar, you can see here. The rear light bars, the bumper pressure mechanism, the outside under vehicle lighting. We've got some red glowy lights under our steps. All right, and then this page here is just solar production and various power monitoring, but I also have here an analog volt sense on our chassis batteries, or our vehicle's batteries. And times like this, when we're in lockdown for months on end, we don't drive around so much. I need to keep an eye on those batteries and make sure they're topped up, because dash cams and tire pressure monitors, all those things leach power constantly. So I've got this indicating the voltage of our chassis batteries, and I can just click this on, and you'll see up here these two LEDs come on, and that's charging now our chassis batteries until they hit 13 volts, and then they'll kick off again. All right, and lights, I'll just show you again with the keyboard. Got the two handy buttons there, as well as OK Google, turn on the lights.
You got it.
OK Google, turn off the lights.
Okay.
So, not too often do we use that, but if you've got dirty hands and you need to jump in and wash your hands in the sink or something, that's handy. I do have motion sensors inside the truck that I've not been able to connect to this yet, so that'll be a nice upgrade here in the future. And then I also have options for dim lights. You can barely see that up in the room there. And regular and bright. And you can see here I also have a slider for every variation in between, which is handy. And what else can I show you? Air compressors. Ugh. All right, guys, so there's a little bit of a wrap-up video. It's certainly far from done, but lots of room for improvement and expandability for me here in the near future. I might do some videos on that, but for now I'm going to wrap it up at this. I know it's been a really long video, so thank you all for sticking in there. Thank you to all of our channel members who push me to make videos like this. I don't know how many of you realize how much time goes into making such a video. Something that would normally take me 30 hours to design, manufacture, and install these. It's probably 3 times that when I need to set up cameras and take 3 or 4 takes at every single shot just to get my point across. So I really appreciate the channel members giving me the nudge to do a good job and make thorough videos, because it is fulfilling once I've done it. Just, it's a little bit painful in the moment. But thank you to all of them. Their names are flown by just now. Thanks so much for watching and tuning in. See you next time.